All right, AP Chemistry students, this is going to be our Unit 10 work. Now, if we look here, we see that it only says Chapter 15. We are also in Unit 10, and there's two chapters of Unit 10, so it's important to see the distinction there. Here are the four different learning objectives we're going to do. Remember that learning objective 0 is some pre-work that we have to do before we can do the rest of this. So it's important work, but there's not going to be a quiz over it, and I'm going to go through that super fast in this. Strength of acids, pH, and acid-base characteristics are the three different learning objectives that we're going to go through and that you'll be quizzed on. Properties, we have the different properties. Definitions. Here I do want to say real quick, if we have an acid here that doesn't give us the chemical formula, we use HA. If we have a base that doesn't give us a chemical formula, we use the A minus, and then we're able to go forward with that. So keep that in mind for later. Ionization steps, we're good with those. We practiced those in class. And just standard stuff from a long time ago. Bronsted acids and bases, a new definition, and then we can see the red ones are going to be acids and the blue ones are going to be bases. Conjugate bases of the acids, we're going to be taking away a hydrogen. The other way around, we have the conjugate acids of the bases. We're going to add a hydrogen. Diprotic, triprotic, learn objective 1. So when we talk about the strength of an acid, we're talking about how much it dissociates in an aqueous solution, not how dangerous it is. So strong acids dissociate 100% while weak acids do not. Same thing with bases. Strong bases dissociate 100% while weak bases do not. So that is what we want to keep in mind. And actually, the weak acids and bases dissociate just a very small amount, like less than 5% usually. So there's a huge difference between the dissociation amounts of the strong acids and the bases as well as the weak acids and bases. Relative strength, if you're going to test those, just check the conductivity. If it conducts well, you have a strong, since strong acids and bases are strong electrolytes, it's going to conduct electricity well. If it's a weak acid or weak base, it's not. We have Ka and Kb and how that relates to strong acids and strong bases versus weak acids and weak bases. So if we look at this, let me see if I can get a little space here. So if we look at this in terms of the equilibrium expression, let's say we have an acid HA. We have hydrogen and the conjugate base. If we have an equilibrium expression of that, that's going to be H plus A minus over HA. If it's a strong acid, it's going to dissociate 100%. And so this value is going to be very, very large. This number is going to be small. In fact, this number is probably going to be 0, which means that the Ka won't exist. So it's just that if we were to go through and see some very, very strong acids that dissociated just very close to 100%, we could get a Ka, but it'd be approaching affinity. So normally we don't express Kas or Kbs for strong ones. Where if we have a weak acid or weak base, that means we're going to have a larger quantity of our original substance and smaller amounts of the ions. And so our Ka is going to be small, or our Kb will be small. Darn it. All right, so explain why strong acids will have a weak conjugate base. It's the same thing. So if we look at this here, this is a double arrow here. If we look at this from the forward direction, if it's, say, a very strong acid, then the numerator is going to be very, very large. So I'll put large here, which this is a strong acid, which means that Ka is going to be a big number. Where if we reverse the reaction, look at it the opposite way, that means that this part here is still going to be, this part here is going to be very large. But now it's in the denominator. So we have a fraction with a large number on the bottom, which means that this is going to be small number. So that's why we have the opposite that's true. So we can look at that. All right, so hydrofluoric acid is a weird acid. It's the only halide acid that does not dissociate 100%. It's the weak one. And the reason for it is actually quite complicated. So we don't get into all of the information of why hydrofluoric acid is a weak acid. Two of the things that we do discuss, though, is this atomic size. Fluorine is a small molecule, which means that it has a better ability to pull on the electrons from fluorine, keeps it bonded together better. But the other part of it is the hydrogen bonding. We know from our intermolecular forces unit that if we have something like hydrofluoric acid, it can go through hydrogen bonding with water. So we have HF, and then we have water here, and then a water molecule here. And there is these attractive forces between those different. They aren't bonds, right? They're just intermolecular forces. And it turns out that that releases a lot of energy, this does, and that helps keep the hydrofluoric acid bonded together as opposed to dissociating. And the greater detail of why this is the case is beyond what we study in this course. All right. 6 strong acids. Here they are. Memorize them. Remember the asterisk is here for the sulfuric acid because it's only the hydrogen that dissociates 100%. Strong acids are strong bases. Weak acids are weak bases. So go through here and identify them. The red ones are going to be the strong ones. The orange are the weak. And same thing here. Blue are the strong. The light blue, or I guess turquoise maybe, is the weak. All right, now we get the molecular strength stuff. This is my favorite stuff of this learning objective, and it's a lot of explanation stuff. All right. So we have hydrogen iodide and hydrogen chloride, or hydroiodic acid and hydrochloric acid when they're aqueous. And when you explain why hydroiodic acid is stronger than hydrochloric acid, we have to follow this kind of rabbit hole of connected concepts. The first one is that the strength of an acid is determined by how easily it ionizes in that aqueous solution. So that's the important part, how easily that hydrogen pops off. So start with that, start with the definition, then go from there. We can start talking about the size of the atoms here. So iodine has a larger atom than chlorine. Since iodine is larger, so here's kind of my representation. There's my iodine, and here's my chlorine. This is a very diffuse electron cloud, and there is shielding going on between the nucleus of the electron cloud and the attraction that it has with the hydrogen atom. And so this shielding prevents the nucleus from being able to attract the electron from hydrogen, makes this bond weaker, and the hydrogen is more easily removed. It ionizes. Where this is a smaller atom, that attractive force is greater, keeps them bonded together better. All right, so now we can go on to the next part, which is on oxidation state. So if we look at these two different things, first of all, the Lewis structure is really important in this. So we have the chlorine, oxygen, 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 hydrogen. This hydrogen right here is the hydrogen that's going to ionize. Well, that's silly. That is where the hydrogen is when it ionizes, not bonded to the chlorine, not the carbon, chlorine. So we're looking at this bond right here. And we can do it for the other one as well. We have chlorine, 1, 2, 3, oxygen, oxygen, oxygen. There's the hydrogen. Again, that's what ionizes. And then it's this bond. So the weaker that bond, 0.01, the weaker this bond, the stronger the acid. Now it turns out that when we have higher oxidation states, this has a +7 oxidation state, this has a +5 oxidation state. There's a greater attraction, a greater electrostatic attraction between the central atom and the oxygens that's bonded to it. So we have a greater positive charge greater attraction to these things. Since there's a greater attraction to these oxygens, that means that it weakens this bond, and that bond becomes easier to break. The hydrogen pops off. A lower oxidation state, it is less attracted to those oxygens, so this hydrogen becomes more strongly connected to this oxygen. It's more difficult to ionize. All right, so there's that one. Now we can go on to this one here. We have different central atoms. So let's circle those central atoms so we can see them. But we have similar oxidation states. So each of these are going to have an oxidation state of +7. And the Lewis structure for these guys look like this. So I'm going to do Z for the central atom for tellurium, selenium, or sulfur. So it's just a generic thing here. We have oxygen, 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 oxygen. Boom, 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 boom. Hydrogen and hydrogen. So that's what each of these looks like. And so when we talk about this, we're only going to focus on one of these hydrogens because the second one is always going to come off more or less easily. And we don't get into why that's the case. It's just the first one we're going to talk about. The higher electronegativity of the central atom, the more pull it's going to have on those oxygens. So this is a high electronegative central atom, like sulfur is going to be the highest compared to these because it's highest up on the periodic table. So it has a greater attractive force to those oxygens. Since it has a greater attractive force to the oxygens, it again weakens this bond. When this bond gets weaker, it breaks away. So higher the electronegativity of the central atom, the stronger this bond, weaker this bond. So that's why this is easier to ionize. All right. There's some other ones here to practice. I only explained the ones that were different. All right, learning objective 2 on pH. The first thing with pH we need to look at is the autoionization of water. And this is the way I like to express autoionization of water because it is simpler. So we have this one here where it produces hydronium ions and hydroxide ions. This is the same thing just with one water instead of two. So we end up with the two different pieces of water, and now we can start to see why the definition of areneous acid exists and base, because we have both parts of it. We have hydrogen ions and hydroxide ions. If this increases, we get an acid. If this increases, we get a base. So it has to do with the basis of what water is made up of. All right. So we have the autoionization of water here. Each of the concentrations of hydrogen and hydroxide are the exact same thing, and we get the equilibrium constant of this. So, oh goodness, that's kind of a big deal. These are negative numbers. Negative, negative, negative. I need to change that on the answer key. So those are all negative numbers. We can see from these negative numbers, though, that we have very, very small numbers for the concentration of hydrogen and hydroxide. So we have very small concentrations of these guys that it barely ionizes. So we've always said that water is a non-electrolyte. Well, it's a very, 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 very weak electrolyte. So weak that we only really care about it or only discuss it when we talk about the pH of acids and bases. The reason why it matters for the pH is this. pH is defined as a negative log of the hydrogen ion concentration. So if we have the hydrogen ion concentration here, we plug it in, we get a pH is equal to 7. That pH of 7 is the basis of water being neutral. All right. Why is it appropriate to use the pH for the acidity rather than just look at the concentration? And there's two reasons. First, it takes this huge abstract number of like 1.0 times 10 to the minus 7th and represents it in a way that's tangible. I can think about it as being a 7, a 6, a 5, something like that. But when we start dealing with scientific notation of like times 10 to the minus 10th or something, it just becomes very difficult. Also, the scale, since it's logarithmic, allows us to express a huge range of values in a much smaller range from about 0 to 14, rather than from like 0.1 to 0.0000, so on to 1. So you got that. There's the autoionization of water and how it's related to the pH. Just talked about that. Oops. pOH and pH are exactly the same, only pOH is looking for the concentration of the hydroxide ions. And then this relationship is really important. Right here. Anytime that we work with a base, we solve for pOH first, and then we can convert it into pH. 26. Let me get my workout. So we have this relationship. Remember, Kw is equal to the hydrogen ion concentration and hydroxide ion concentration. So if I have a hydrogen ion concentration, remember, strong acids dissociate 100%, so whatever we have of hydrochloric acid is also the concentration of the hydrogen ions. So these two things are exactly the same. Plug in this guy for the hydrogen ion concentration, and we plug in 1.0 times 10 to the minus 14th for water, 1.4 times 10 to the minus 3rd x, and then we can plug in and solve for the hydroxide ion concentrations. It turns out the hydroxide ion concentration is going to equal 7.1 times 10 to the minus 12th. They're inversely related. One goes up, the other one goes down. We can do the exact same thing for number 27. We end up with an answer of hydrogen ion concentration equal to 1.6 times 10 to the minus 14th. So those are those. Erase. All right. pH of strong acids and strong bases. So those are the three different mathematical relationships we need to memorize. If it's a strong acid, all we have to do is to take that hydrogen. I bet you just yawned right then, didn't you? If you're listening to the sound and I yawned, you probably did too. Anyway, so we have hydrogen ions in this hydrochloric acid equal to the concentration. And just one more time to make sure. That's because this thing dissociates 100%. Since it dissociates 100%, whatever concentration I have for the hydrochloric acid is the same concentration of the hydrogen ion. Negative log 3. This one here, be careful, it's 13.88 because you have to take your answer and subtract it from 14. Notice the typo here, there should be an H there for the hydroxide. The barium hydroxide problem is a little bit different. Notice that when I start with 2.8 times 10 to the minus 4th for the concentration, but I have 5.6 times 10 to the minus 4th here for the concentration of hydroxide ions. And that is because when barium hydroxide ionizes, we get 2 hydroxides. So I have to take this value and multiply it by 2 to get the hydroxide ion concentration. pOH, subtract, get pH. This one's very straightforward. Plug in and get your answer. Now we can go backwards. We're looking for the hydrogen ion concentration now, and we need to then use the opposite of log, which is 10 raised to the power, so 10 raised to the negative pH. Plug in the 4.6, we get an answer. The reason why I use 4.6 is because it's the pH. We're looking for hydrogen ion concentration, which is the pH, not pOH, so we have to do that calculation ahead of time. All right, now we're into the difficult stuff. Ish, not too bad. We've already talked about this one. Number 21 is going to be our benzoic acid problem, and this is going to be our first problem related to ice tables on this thing. So we need a Ka. It tells us that. Remember that weak acids are ones that do not dissociate 100%, so there's going to be an equilibrium there. So we have a Ka, and that Ka is equal to 6.5 times 10 to the minus fifth. My benzoic acid equation is C6H5COOH, and that splits up into the benzoate ion and now we can set up our ice table. We have an initial concentration of 0.100. We end up with an equilibrium of 0.1 minus x, x, x. This is plus x minus x. Now we can set up our equilibrium expression. Ka is equal to the benzoate ion, which is just so much fun to write over and over again. And one more time, C6H5COOH. We can plug things in now. We have our Ka of 6.5 times 10 to the minus fifth is equal to x squared minus 0.1 minus x. And I'm going to go ahead and use the approximation on this one. Approximation means that I can get rid of that. And so it makes my math a lot easier, so I don't have to use the quadratic. X turns out to be 0.0025. And if we wanted to do the approximation check, 0.0025 divided by 0.1 is going to be not very small number. It's not going to be anywhere close to 5%. And that is equal to our hydrogen ion concentration. So remember X right here. It's our hydrogen ion concentration, 0 plus X. Have our hydrogen ion concentration. That means that our pH is going to be 2.6. Simple enough. Now I think for the rest of the acids we can't use the approximation. That's kind of a pain in the butt. I did use an equation solver online rather than trying to deal with the quadratic. So I expect you would do the same if you had a TI-89 or something like that. All right, number 22 is a little bit more involved because we're not given a concentration, we're given a mass. 0.056 grams of acetic acid. Let's figure out what acetic acid is first. This one right here. It's written weird. CH3COOH. 0.056 gram of a sample of acetic acid is dissolved in water to make a solution so we can get molarity from that. First we have to convert the 0.56 grams, 0.056 grams into moles. And it turns out to be, I think I'm going to have to redo this problem. 9.3 times 10 to the minus fourth of CH3COOH. Now, when I did this problem on my answer key, I just used this value for all of my work. I didn't use the concentration. So hold on a second. I'm going to have to calculate this out as I go. So we have 9.3 times 10 to the minus fourth divided by 0.05. That gets us a value of, that's our liters by the way, 0.0186 molar. And you know what? I think maybe we will be able to use the approximation on this one now. So we have that for a concentration of acetic acid. We can do our ice table, CH3COOH. We end up with a Ka for this thing. Yeah, the approximation should work on this one. Let's find out. If it doesn't, I'm not going to go back and do the quadratic. We're just going to leave it unfinished. Times 10 minus fifth, second square root. Yeah, we're at 3%, so we're good. So x is equal to 5.79 times 10 to the minus fourth, which is going to equal our hydrogen ion concentration. So the pH is going to equal 1.5. All right, so there's that. Let me take a second here. Scribble, scribble, scribble. I have to redo that on my answer key. All right. Now we're asked to go the other direction. We have a Ka that we're looking for, and we have a pH. So we are going to have to solve for the Ka. Well, obviously, but we have, let's do, we first have our equation. It doesn't tell us what acid we're using, so we can't look up the Ka. All we can use is this to figure it out. And the Ka is equal to this. If we have all of this information, then we can solve it, right? That's the whole point. We have this 0.01, we have this 0 and 0, and we have this too, right here. We have the equilibrium concentration of the hydrogen ions. This is minus x, this is going to be plus x, this is plus x. And here is why we know this. The pH is equal to negative log the hydrogen ion concentration. So if we rewrite this thing, we know the hydrogen ion concentration, which means that we also know x, because the hydrogen ion concentration is 0 plus x. So if we plug things in, 10 raised to the negative 6.2, we get a hydrogen ion concentration of 6.9 times 10 to the minus 7th. So there is my x, and now I can plug that into the Ka expression. So we end up with Ka is equal to 6.93 times 10 to the minus 7th squared, 0.01 0.01 minus that number. Really, that's just going to be 0.01, but I'll show the work. And you're taking 0.01 and subtracting 0.0000069, and so it's going to come out to be 0.01. So the Ka ends up equaling 5.74 times 10 to the negative 6th. So that's how you do that kind of a problem. Next up is percent ionization. I'm going to do the first problem with you guys, and you guys can do the rest on your own. I'll give you the answers here first. The first one is going to be 3.4%. Next one is 32.4%. The last one is 75%. Here's what I'll tell you too. Number one here, you can use the approximation. The other ones you can't. So you either have to use the solver or quadratic for those. So for the first one, you have HF. And that should be obvious, right? Because if the percent ionization is more than 5%, we can't use the approximation. So here's that part plus F. We just solve, right? We have the ice table. Start with 0.06 or 0.600 minus x plus x plus x 0.6 minus x. I always show these ice tables, even though the same thing over and over and over again. It really helps me organize the information and make sure that I do my math right. So we have a Ka for this thing. Ooh, yeah, we used this. Have we used this one before? I thought we used this one before. Ka 7.1 times 10 to the minus 4th. Plug that in. We have 7.1 times 10 to the minus 4th is equal to x squared over 0.6, sorry, minus x, but I'm using the approximation, so x comes out to be, do I not have an x for this one? My goodness. All right. 7.1 times 10 to the minus 4th times 0.6, second square root equals 0.02. Yeah. 0.021 molar is equal to our hydrogen ion concentration. So for the percent ionization, we're going to take this value, 0.021, that is the concentration of the hydrogen ions, and divide it by the initial, which is the hydrogen fluoride. And so that's how you solve for how much of it ionizes. What you get divided by what you started with, 3.4%. You do the same process for the other two, only in this case, you can't use the approximation. You have to use the solver or the quadratic. All right. Ammonia. Oh, you know what? These three problems are going to be exactly the same as what we did before with the acids, only with bases. Ooh, that's exciting. All right, so let's go through, and I'm going to do these a little bit more quickly now. The biggest issue that students have with bases is writing out the ionization process. Remember, with bases that are weak, you always have to put them in water, because water is the source of the hydroxide ions. NH3, oops, NH4, OH minus. We have our ice table, 0.100 x, 0.1 minus x, Kb, ooh, Kb. We have our we have x squared over 0.1. We're using the approximation. The Kb for this is, we use it all the time, I have it memorized, is that solve for x, we end up with 0.0014, which means that is the concentration of the hydroxide ions. The pOH then is going to equal 3.87. pH is equal to 10.13. There is our final answer on that one. Some things to be aware of: we're using a Kb instead of a Ka, so when we solve for a concentration, which is X, we're solving for a hydroxide ion concentration. And we have a hydroxide ion concentration. When we take the negative log of it, we end up with a pH, a pOH. pOH. To get to pH, we have to subtract from 14. All right. Number 26 is going to be the same thing, only you won't be able to use the approximation. Wait, that is a lie. You definitely can. All right, I'm going to just give you guys the overall equation for this, because this pyridine stuff is kind of weird. It looks funny. Now, all we have to do is remember that we take... how would you know that? All right, so the first question is, how do we know if this is an acid or a base? It's organic. It doesn't end in COOH, so it's probably not an acid. But what happens if maybe the chemical formula was just written weird? It also doesn't look like a base that we've talked about before. We have like our organic chain and NH2. That has been also an indicator. So the only way that I guess you could come up with and figure out that this is an acid or a base is to look it up. If you weren't sure, it is a base. And so when we show this thing, we have, and I won't, like, I'm not going to be sneaky on these quizzes. I'm not going to try to give you something that you don't know if it's an acid or a base. The other thing that could happen is that I'll give you a KB a lot of times. And if you get a KB and not a Ka, you know it's going to be a base. So the KB for this one is 1.7 times 10 to the minus 9th. So there's that. We have C5H5NH. We're going to put the hydrogen onto that nitrogen just like we do with ammonia. We end up with hydroxide ions. Do your ice table, same thing. With this being the Kb, you can definitely use the approximation. The X value here for hydroxide turns out to be 9.22 times 10 to the minus 6th. POH ends up being 5. pH is 8. So there's that one. So this one is identical to problem number 23, only instead of trying to get a Ka, we're trying to get a Kb. So again, I'll do this one more quickly. When we're dealing with a base, again, we use A minus. We get HA on this side, hydroxide there. So here's my ice table. I end up starting with a concentration of 0.30. Water goes away here. And we have the concentration of our equilibrium hydroxide. These are 0. 0, 0, plus X plus X. So if we have this, we also know what X is. You have to be careful with this problem though, because we're given a pH and we have a hydroxide ion concentration. So before we can do the rewrite, we have to do this. pH plus POH is equal to 14. That means that our POH is going to equal 3.44 or 3.34. So if I have a POH equal to 3.34, I can do 10 raised to that power. And that gets me my concentration, 4.6 times 10 to the minus 4th. Now, I have this here, 4.6 times 10 to the minus 4th. Same thing here. 0.3 minus it. Now we can plug into our Kb equation. And we end up with a Kb equal to that guy right there. Number 28 is going to be a percent ionization problem. So it's going to be exactly like these problems we did with the acids here. Only it's asked a little bit different. It says percent ionization of this guy, hydrogen fluoride, hydrofluoric acid, In this case, it asks us for the percent of the solution of that. Well, if we look at the ionization process, solving for this in a percent is the same thing as solving for percent ionization. We have our ice table. We have our initial concentration of 0.8. Water goes away. 0, 0. We go through all of the same processes we've done before. For Kb is equal to x squared over 0.08. We can use the approximation for this one because the Kb, or can we? Yes, we can. Is equal to 1.8 times 10 to the minus fifth. So x comes out to be 0.0012. And that is going to equal our hydroxide ion concentration. And it's also going to equal then our ammonia concentration, because both of those are x. We solve for x, we have both of those. So if we know our percent of hydroxide, we know our percent of ammonium ions. Divide this by 0.0012 divided by the original 0.08. That gets us 1.2, 1.5%. So there's that. All right. That should be the end of learning objective 2. So now we have learning objective 3, which is the acid-base properties of salts and oxides. Before we start here, the acid-base properties of the oxides are not as important as the salts. Now, they both are important, but to be able to be successful in the second part of Unit 10, learning objective, chapter 16, you have to understand how a salt can be acidic or basic or neutral, where the oxides don't come up again in AP chemistry. So I'm going to spend some time here and discuss why. I'm going to choose 3 of these to go over and discuss why it's an acid, a base, or neutral. So I'm going to use this area right here to be able to answer that. So hopefully you're not confused. I'm not answering this question yet. I'm answering the question up here. All right. First one. This one is going to be a base. Blue is base. I used red. So the blue is going to be our base. Green is neutral and the red is acidic. We'll start with the base first, and here is why. Going back to our solubility rules in chapter 4, we know that if it has an alkali metal, it's going to be 100% soluble, meaning it dissociates into its ions completely. Let's say we have a concentration of this of 1 molar. That's where we're going to start. We have then CH3, COONA, single arrow because it dissociates 100%, CH3, COO plus Na. This right here is the conjugate base of a weak acid. This thing right here can go through another ionization process. So if I have 1.0 molar of this, that means I have 1.0 molar of this. So I can go CH3, COO. It ionizes with the water in the aqueous solution. we end up with the hydroxide ion. And our initial concentration here, which we're going to be doing when we do question number 34, is going to be 1 because it dissociated 100%. Now I can go through a process just like we did previously. So when we identify this, we look for the conjugate of a strong base and the conjugate of a weak acid. So if part of it is the base part, so not conjugate, part of the base. So we have it's made up of a strong base and a weak acid. It's the language we use. Hold on. Yeah, that happened. All right. If it's made up of a strong base and a weak acid, it's basic. So we have to look at what different pieces it comes from. So the piece here would be sodium hydroxide. The piece here would be acetic acid. So we have a strong acid, strong base, strong acid. So if we have a strong base and a weak acid, oh my goodness, I apologize. Strong base and a weak acid, it's going to be basic. And this process is why, and I'll show you how to do this problem then. Alternatively, NH4 is made up of NH3, that's the basis of it, that's the piece of it, or NO3 is made up of nitric acid, HNO3. So here we have our strong acid piece and our weak base piece. So we end up with an acid, and that'll be number 35. If we have something like this, the sodium chloride, where we have NaOH, which is a strong base, and we have Cl, which its counterpart would be HCl, would be a strong acid. So when you look at this, you look at it in terms of whether or not it's a positive charge, a cation, or an anion. If it's a positive ion, you're going to look to see what makes sense in terms of its piece. So sodium, it's going to be with hydroxide. Here with this cation here is going to become ammonia. So the cations are our basic piece, where our anions are our acid piece. So look at the anion here, NO3, we have to make this an acid, nitric acid, HNO3. Our chlorine, we have to make it an acid, it's our anion, the HCl. We have our acetate here, CH3, so again down here, we have to make it the acid piece, which would be acetic acid, that's a weak acid. So that's how you can go through and identify which is which, either acidic, basic, or neutral. This takes practice. But it's super important because we use this concept right here in chapter 16 for 80% of the chapter with the work we have to do. So we're going to go through these problems slowly. All right. Well, I got 2 problems left pretty much, then we're done. I'm going to use blue. Is that right? Yeah, I'll use blue. So we have CH3COO. So here is our initial dissociation process. Because we have an alkali metal, it dissociates 100%. Quick ice table, Ce, start here at 0.36 minus 0.36 down to 0 because it dissociates 100%. Over here, 0, 0 plus 0.36 plus 0.36. So it breaks down into those pieces. We can then use this guy here as our basic piece. It's in an aqueous solution, so there's water around, right? So there's the water, CH3, COOH. There's our ice table, 0.36. Water goes away because it's not, it's a liquid, it's pure liquid, 0, 0. And then we can go our minus x plus x plus x, and then it becomes identical to what we've been doing before. The Ka, I don't want to get too confused here, Kb of this thing is equal to 5.6 times 10 to the negative 10. So now we have what we need in order to be able to solve for this. We have a Kb, which is 5.6 times 10 to the minus 10th. Is equal to x squared divided by 0.36. Going to use the approximation. X is equal to that's unfortunate. 1.42 times 10 to the minus 5th. Ladies and gentlemen, if I had made this mistake earlier on in the video, I would have gone back and started the video completely over. And it's right here. This is hydroxide. So we have a weak base here with water. We get our acetic acid hydroxide. So thanks for making it through that problem with me, and hopefully you caught that problem sooner than I did. So there's our concentration of hydroxide ions, which means that the POH is equal to 4.85, and pH is equal to 9.15. So there's that. All right. I'm going to do a better job of not messing up on this last one. Darn. All right. We're going to go through. pH of a 0.42 solution, not a 42 molar solution. That wouldn't be possible. All right. So we're going to use red this time because this thing is an acid. NH4. Since that ammonium is there, ammonium ion, that means that it's 100% soluble. Quick ice table to make sure we see how this works. 0.42 minus 0.42 is 0. Single arrow, strong electrolyte, goes to completion, don't have any left. 0, 0. And there you have the initial concentration of what we're going to be working with. The Kb for NH4, Ka. Now this is just a weird coincidence with these two different problems. The Kb for the last problem was 5.6 times 10 to the minus 10th. The Ka for this thing, the NH4, the ammonium ion, is the exact same thing. So just a weird, odd coincidence. So plug things in. 0.42 minus x now becomes what we know. So we have 5.6 times 10 to the negative 10th is equal to x squared over. We can use the approximation on this one again. So I'm going to go ahead and do that. We end up with an x value of 1.5 times 10 to the minus fifth. It means our pH is going to be 4.81. There's the answer there. Now the oxides. And here's kind of what we need to know. The nonmetal oxides are going to be acidic, where the metal oxides are going to be basic. And in class, we looked at some of the equations that we can write with these. And I'm going to do the sulfur dioxide and the magnesium oxide as examples. So if we have the sulfur trioxide, SO3, remember, these are always aqueous. Actually, I'll do them both. This is going to be then, my goodness, put this guy with the water, H2SO3. So we're just making the acid out of it that is based off of whatever polyatomic ion this is. So like P4O10 plus water would make phosphoric acid. And then we would have to balance this thing out, however that works. But that's the process of these. And I don't know if this is something that we really need to know. Like, it doesn't come up again during the course of the year. I don't think it's on the test, really. It's just some additional chemistry knowledge that we can look into. But this part you do want to know. The non-metal oxides are going to be the acids, where the metal oxides are bases. So we have our bases here. So here we have like magnesium oxide plus water. It's going to make magnesium hydroxide. Sodium oxide plus water is going to make sodium hydroxide. Now these things aren't balanced, so don't worry about that. But we end up with our hydroxides with the metals. And then the one that's amphoteric is going to be the aluminum hydroxide here, or aluminum oxide. And so we don't really do any kind of reaction with that one. So there you go. All right. Thanks for watching.